Swayam Prabha. Digital India. Educated India.
Welcome back to the you can say mechanics and control of robotic manipulator. Last class we have seen like how the task space you can say motion control can be done in Matlab simulation. This particular lecture is actually like in addition. So again we are trying to do the Matlab simulation, but with what you call the cascaded or the double loop control scheme. So for that, what we have seen in the lecture, so in the regular theory we have seen there would be two error. So E1 is actually like mu decide minus mu, where E2 is actually like q dot decide minus q, where the q dot decide is not directly derived from the inverse kinematics or inverse differential kinematics. In the sense what we are trying to do, the initial loop what you call the outer loop would give the desired value for the inner loop. In the sense the q dot decide would be obtained from the outer loop, which we have written as q dot decide as Jacobian inverse into mu dot decide plus k1 E1. So based on that, what we have actually like derived the tau, which is the control law. The control law, or you can say control scheme, is derived in this way, where the matrix inertia matrix multiply with q double dot decide plus k2 E2 in order to make the stability J transpose E1, plus in order to make the feedback linearization we have added n of q comma q dot. The same thing we have tried to do it in Matlab. So in the sense what we have done here is, so we have actually like make the same code. So only thing we have added a few value. So for that we have taken the same code and we have added the k1 and k2 instead of you can say kp and kd. So now this is the added value, and the mu dot decide, mu double dot decide all are same, just to give the you can say simple comparison. Then you can see like just for our understanding, so this q decide we have actually like derived. This is not for the control scheme, this is only for for plotting or just for comparison. So further we are actually like taking the actual dynamic terms, and then you can see the other entity which is required, because we need to know like inverse Jacobian dot and Jacobian, all those things. So we have actually like used this. So why we need inverse Jacobian dot? Because if you look at it, this equation, so if you are actually like taking q double dot decide, which is required here, so then that would be j of you can say j q inverse into mu double dot decide plus k1 E1 dot plus j dot of q inverse into mu dot decide plus k1 E1. In the sense you need j dot you can say inverse of j q dot is required. So that's why we are actually like writing it here, that value. So in the sense we are adding one additional sub function. So that is what addition to the existing control code whatever we have seen in the earlier class. So in the sense this is the inverse Jacobian dot what we have actually like done. So this is the full function, we can see it in the Matlab. So now I just want to add that there is a sub function which we have added. So now come back to the mu tilde. So mu tilde here actually like mu decide minus mu, which is actually like you write as a E1. So E1 dot is actually like mu dot decide minus so mu dot. So the mu dot we can write as a j multiply with q dot. So this is nothing but a mu dot. So after that what we have come up, so we have come up with a q dot decide, which is actually like what derived based on the outer loop. So which is inverse of j decide multiply with mu dot decide plus k1 E1. So based on that we calculated E2. So E2 is actually like q dot decide which we derived minus q dot. So after that we are going with the double loop. So where the double loop you can see like whatever we have written in this equation, this equation we are straight away using it. Okay. So in the sense what we have actually like found, so where the m of q multiply m of q we have written here as m. So inverse of Jacobian decide, that is we have found, and the mu double dot decide plus k1 E1 dot. Okay. So then you can see like there is a minus that I have to correct it. So minus j you can say dot decide inverse. So that multiply with mu dot decide plus k1 e1. So this is a minus sign, so I will correct it. So k2 e2 j transpose e1, this all will come inside. Then you can see like the other effect, which is actually equivalent to n of q comma q dot, which is together as other effect vector plus gravity. Okay. So in that sense, this is actually like going to give the control law. So you can actually like look at it. So what we derived, so this is the equation. So this equation actually like, yes, it is a plus sign only, not a minus sign, because this is q dot decide, we are actually like differentiating, right. So in the sense plus sign, so that is actually like maintained here. So then we can actually like go to the acceleration, velocity and position update, which we have done in the earlier, the same thing. So then we can actually like go to the final just to plot. So what is the error in you can say outer space. So that is what we are trying to see. In that sense, we go to the Matlab code. So where we call CCD, which is actually like cascaded control design. So this is the you can say the dual loop control. So initial as similar as the simulation parameter, the system parameter has come, then the gravity we included, and the initial condition is random initial conditions we have included, and the k1 and k2 we assume as 4. Then the mu dot decide, mu double dot decide, all derived as h. Based on that, just for our purpose, we have taken the inverse kinematics. Then the j decide we have calculated based on that. Then j dot decide based on the you can say original case. So this is just for our idea, but the second thing what we are using it inside the loop. So we have taken this way. Okay. So now we can see E1, E1 dot and E2 we calculated. Then the cascaded control has come here, m into so and so. Then these all actually like based on what we have derived there. So then we can actually like come back here, simple Euler integration based on the acceleration. Then you can see so the animation part, then the plotting part, and then the sub functions all. Okay. So the additional sum function we have added here. So the remaining all are actually like same. Okay. So in the sense, if I run, so the same philosophy will be used. So we assume that non-zero initial error and the circular profile we are trying to follow. Okay. So we are actually like trying to see that. So you can actually like see it this way. So we can actually like find it this. So now if we talk about the error, it is actually like very smooth. Okay. So now we are actually like even introducing something like a small you can say hiccup, in the sense this is actually like only 0.9%. I don't know, like 90% would be converged, it may end up with unstable. So you can see like it is trying to follow, but still the you can say it is a model based control. So that's why you can see the error is coming. So now in order to increase the performance or improve the performance by reducing the error, either you can increase the Kp Kd value, or in this case K1 and K2 value, or we can actually like introduce the integral error. But the cascaded control design we did not see the integral error. So what we can do, we can actually like increase the K1 or K2. So one is actually like beneficial because outer loop. So I am just increasing the K1 value just for our benefit. So we can see whether it is actually like improved. So it is actually like slightly improved, you can see, right. It is not completely better, but slightly improved, because we have compensated only 90%, right. So now you can understand why it is called model based. If your model is inaccurate, you can see it is not tolerated. So now if I actually like make it, this is 95% or probably 99%, it may actually like converge very fast. You can see like it is actually like going very close. So even you can see a small error, but you can see the error is actually like improved, right. So this is what we can actually like see. So why the gravity need to be compensated, you got idea, right. So now this is actually like one thing, but the other effect vectors are actually like not that significant. Even if I actually like make it 0, you can see like that is not contributing, because it is very small, because the system is actually like moving in very slow speed. Your centripetal and Coriolis term is not that significant as the gravity. Okay. So that is what the whole idea. So now I hope you are actually like clear what the cascaded control design all about. So now if I actually like change, So change in the sense I am just trying to see, probably trying to see this can happen or not. I am just trying to see the 0.4, in the sense 0.8 can come, but 0.0 is not obtainable, because so if the sign is -1, what happened, this is 0.4 minus 0.4, okay, in the sense it is 0, but what happened, your workspace, so workspace is actually like, you can see the inner circle is, so A1 minus A2, in the sense 0.1 is the inner circle radius. So that's why it is giving, even in the previous lecture we have tried to do it, right. So it is giving unnecessary thing, because this is actually like not substitute or not possible, right. So in addition to that, if I actually like improve this, so in the sense it may touch the outer, it may work, okay. So we can actually like see this is also not working, because it is extended to the final touch, but you have the J inverse, right. So final touch in the sense 0.5 plus 0.4, when this is actually like become 0, it is the entire workspace extended boundary reach. So that is make it as a one additional singularity. The other one is not possible, task space. So the other one is actually like end up with what you call the boundary singularity. So in the sense the Jacobian would be, you can say like a singular one. So in the sense this is also not possible. So now you got why it is actually like not getting it. So you have idea, right. So now the similar direction I am trying here. So I'll just make it, this is 0.1. So 0.1, maybe you can say 0.2 itself, but this is 0.1 I am trying. So I hope this will work. I hope so. So I am not clear whether that 8 profile can be generated here. So I am just trying to see that. Yeah, you can see like I am trying to follow a 8 profile. If I increase the you can say the time range, it will actually like make 8 profile. So you can actually like see, if I increase the time, which is actually like I will give 60 seconds. So you can see like it actually like make a 8 profile, okay. I think it is not, because there is a converge, right. The converge end is actually like making it. So I am trying to show that, so where it can end up. So where this point is actually like intersect that middle point. So 31.4, right. So I will just put 31, you can actually like see it, it is coming closer, okay. So when this point is actually like started, so the workspace is actually like getting somewhat singular, okay. So that's why it is not coming in. So I'll just make it, this is 0.4 itself, okay. So now I'll just make it, probably increase the time. I just want to see whether that 8 profile I could show you. No, it is not possible. So then I can actually like make it at least, so this 8 profile, the half of the 8 profile we can actually like see. So in order to make it, probably I have to bring the y. I'll see whether that is possible, because the solution may actually like extend, that also can go. So I am just saying that this is probably 0.3. So then the y can go 0. So you can see like this is actually like trying to follow a 8 kind of profile, so which is a spiral, you can say. So now you can see the cascade design, where you can actually like change your K1 and K2, the performance will vary. And similarly, even you change the model parameter, for example this is 5 kg, and still this will work very comfortably. So these all we have actually like tried to see. So with that, what we can see, we have seen the motion control overall go. So where we talked about joint space scheme, then task space scheme. Finally we end up with the merge, which is what you call the cascaded. The outer loop would be seeing the task space, and the inner loop would be in the joint space. So in that sense, the controller, which is actually like going to give a command to the actuator directly given in the joint space, which is much beneficial. The other way around, where you are seeing that the task space need to be followed, that is also ensured. So that's why this cascaded control design is very popular in the modern days, because you can directly control the task space, but the actuator signal directly given on the joint space level. So that is what the whole idea. I hope you have actually like enjoyed this particular lecture. So the next lecture would be on completely different, where we are taking a mobile robot, but we are trying the you can say Danawit-Artenberg approach, how to derive the kinematic and dynamic model, and then see how the controller can be in-house in that particular scheme. So with that, I am saying thank you and see you then. Bye. Take care.